So today we'll be starting mostly with your purines. Today we'll be starting with your purines. Okay. So today purines. As I said yesterday, purines are what? They are nothing but pyrimidine fused to your imidazole ring. Pyrimidine fused to your imidazole ring. So your numbering starts with nitrogen at the side 1, 2, 3, 4, 5, 6, and your imidazole ring with 7, 8, 9. Okay, so this is your numbering of your purines. Very important to be remembered. Okay, C5H4 N4. Okay, so purine is an heterocyclic aromatic organic compound consists of a pyrimidine ring fused to a imidazole ring. So what is purines? They are nothing but an heterocyclic aromatic compound in which a pyrimidine ring, that is 1,3-diazine, which is fused to your imidazole ring. So these are your basic unit of your purine. Purines, including substituted purines and their tautomers, are most widely distributed kind of your nitrogen containing heterocyclic lineages. So they are mostly present. Uric acid, you name it, uric acid, caffeine, adenine, guanine. These are all the basic derivatives of your purine which are present in our body and in the nature. So purine and pyrimidine makes up two groups of nitrogenous bases, including the nitrogen bases, including the groups of your nucleotide bases. So this forms the basic nucleotide bases in your DNA synthesis. Okay, sequencing. So what is the first method of synthesis of your uh, this is one of the methods for synthesis of your purine. So what is the first method for the synthesis of purine? It is known as TROPS purine synthesis. It's known as TROP purine synthesis. This comes for 2 marks basically. Basically, it comes for 2 marks. So what is this? It's a condensation type of reaction. It's a condensation type of reaction. It's a condensation type of reaction. So what happens? Your 1, 2, 3, 4, 5. Your 5, 6. It's wrong. It's okay. It's 5, 6 amino. Sorry. 1, 2, 3, 4, 5. Sorry. 1, 2, 3, 4, 5. Okay. So your amino group should get the least numbering as per the nomenclature. Your amino group should get the least numbering to the substitution. Okay. So that is 4,5 diamino pyrimidine. That you treat it with what? That you treat it with carbonic acid. You treat it with carbonic acid. That is NaCr double bond O. You treat it with the carbonic acid and you heat it. It undergoes dehydration minus water. It undergoes cyclization. Undergoes cyclization to give you your corresponding purine. So it is similar to that of your benzimidazole synthesis, where you took orthophenylene diamine, you treated with different acids, carboxylic acids like formic acid, acetic acid, to get your substituted derivatives. So you get an R substituted derivative. So this is how you prepare your purines. What is you take 4,5-diamino pyrimidine. You treat it with what? You treat it with carboxylic acid group. So it undergoes condensation reactions to give you your corresponding purine derivatives. Okay, corresponding purine derivative. Okay, this is the method for synthesis of your purine. So what are the different derivatives as I explained yesterday only? Uric acid, xanthine, hypoxanthine, and caffeine, theobromine. So these are the various derivatives of purines. Okay, these are the various derivatives of purine. Uric acid means it contains 3-oxopurine analog. Xanthine is 2-oxo, means it has got oxygen oxo group at your second and the sixth position. That is xanthine. Hypoxanthine means it contains only 6-oxopurine analog. Theobromine is methylated oxo dioxo. Caffeine is methylated and methylated oxo dioxo derivative. Okay, theobromine is monomethyl dimethylated that dimethylated this thing. What do you say? Dioxo purine analog. So yesterday we have gone through all these things. So all these things was explained, all the structures was explained yesterday in yesterday's class. But please remember, while give the examples of these things are asked. Examples of purine analogs are asked in your exams. Okay. So now these are the various tautomeric form. So if you see, they are also in keto form. So this keto can be converted into your enol form. So whatever you see, so uric acid, it is in keto form. It gets converted into your enol form. So these are the examples of keto enol forms of your corresponding derivatives. Also, oxide derivatives gets converted to enol derivative. So hypoxanthine, xanthine, and uric acid, they get converted into your OH from your carbonate. So these are nothing but your the present slide represents the tautomeric forms of this thing. So it can be present as your carbonyl form or as an O-ene form. That is your enol form. So your derivatives of your purines can be in both keto as well as enol form. So these are the what are the first derivative? Uric acid means it is a trioxopurine derivative. It is a trioxopurine derivative. Some of the chemical properties, it forms a disodium salts because of the ketoenolic form. Okay, it gets converted into your chlorine. So if the OH which undergoes ketoenol, the OH can be converted into your chlorine form, and this chlorine, when if it is treated with your hydrogen, it undergoes dechlorination to give you a corresponding purine analogs. To give you a corresponding purine analog. Okay. So, what are the reactions of uric acid? Uric acid, what happens? It reacts it on oxidation in came HNO, nitric acid oxidation. What do you get? Your imidazole ring is removed. You get an dioxo form at your fourth and fifth position. You get an dioxo form at the fourth and fifth, and also your urea is formed along with that. And in presence of KMNO4, in presence of alkaline KMNO4, if you see the pyrimidine ring is oxidized, means broken, to give allotone. So you to give your allotone. Okay, these are the two products of your oxidation of uric acid, which is very much important in your various reactions in determination of your uric acid in your chemistry. Next is your oxidation. So it undergoes, next is your reduction. So it undergoes reduction to give you, so your uric acid gets reduced to your xanthine. That means your carbonyl at the eighth position, it's converted, it's reduced, and you get your xanthine. So when you reduce your uric acid, you get a xanthine derivative. Means your carbonyl at the eighth position is converted into your methylene group. Now examples of next class of aminopurines are aminopurines. Examples are adenine and guanine. They are present as a purine bases in your nucleic acids. So adenine and guanine are present as a present in the nucleic acids as purine bases. So what is adenine? Adenine is nothing but 6 amino purine. Adenine is nothing but 6 amino purine. What is adenine, everybody? Can you just recite? Adenine is nothing but your 6 amino purine. So what is adenine? So what is adenine? So adenine is nothing but your 6 amino purine. And what is your guanine? 6 oxo 6 it is nothing but 2 amino 6 oxo purine. It's nothing but your 2 amino 6 oxo purine derivative. Okay, so if this guanine undergoes ketoenol tautomerism to give you your, so this NHO carbonyl gets converted into your corresponding double bond OH. So this undergoes ketoenol tautomerism. The guanine undergoes ketoenol tautomerism. So these are the examples of aminopurines which are present in the nucleic acids as purine bases. All these things are very important in your medicinal chemistry because all the structures are repeatedly will come up in your medicinal chemistry. So these are some of the natural products containing pyrimidine, pyrazole. So please go through this. These are the compounds which are present in your which are used in your industries, pharmaceutical as well as agro industries. So in exam, if they ask, give the examples, you can mention these compounds. You can mention these compounds. Trimethoprim is one of the example. Pyrimidone, 5-fluorouracil, zidovudine. Zidovudine is nothing but an antiviral agent. Okay. So these are some of the examples of your pyrimidine, pyridazine, pyrazines. Okay. Now comes phenothiazine. Now comes phenothiazine. Now comes phenothiazine. Okay. What is phenothiazine? So what is phenothiazine? It is a dibenzo 1,4-thiazine derivative. It is a dibenzo. It's a dibenzo NH. Okay, it's a dibenzo 1,4-thiazine derivative. So it is a dibenzo 1,4-thiazine derivative. So numbering is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Please remember the numbering. It is 1, 2, starts from 1 benzoring, goes to your sulfur and ends with your nitrogen. So this is your structure of your phenothiazine. How it is prepared? It is prepared by treatment of diphenylamine. Diphenylamine, you treat it with sulfur in presence of your aluminum chloride. In presence of your aluminum chloride, it undergoes cyclization to give your phenothiazine. So it undergoes acetylation to form N-acetyl derivative, and it reacts with methyl iodide to form N-methyl 10-methyl phenothiazine derivative and 10-acetyl phenothiazine derivative. So these are the two reactions of your phenothiazine. It undergoes oxidation to give form in presence of KMnO4 to form phenothiazine oxide, that is 5,5-phenothiazine dioxide. Intermediate product is formed. It undergoes electrophilic substitution reaction at the 3rd and the 7th position. It undergoes electrophilic substitution reaction at the third and the seventh position with oxidation of your sulfur. So these are the reactions of your phenothiazine. Some of the examples are aminazine, itapirazine and all, and methylene B, which is an diagnostic agent. Now comes your azapenes. What are these azapenes? Can you count the number of atoms in the ring? So how many rings, atoms, members are there in an azapene? If you can see compounds, they have 7 membered rings. They contain 7 membered ring. Okay, azapenes are heterocyclic of 7 atoms with a nitrogen replacing a single carbon. So when one carbon is replaced by a nitrogen in a 7-membered ring, it is known as azapene. So what are azapenes? They are nothing but 7-membered heterocyclic compound where one of your carbon is replaced by your nitrogen. So let's write NH 1, 2, 3, 4, 5, 6, 7. Okay, 1, 2, 3. Okay, this is a 7-membered ring containing an nitrogen. This is known as azapene. And when a benzene is fused to it, it is known as benzazepines. When a benzene is fused to it, it is known as benzazepine. Okay. So let's go for the next one. This is the basic things that you have to know. It should contain a 7-membered ring. It contains a nitrogen and all. It is known as azapine. When benzene is fused to it, it is known as benzazepines. So these are the basic things that you have to know of azapenes. Now let's go for the naming. So as we have studied in your heterocyclic, when we are studying, so when it contains maximum number of double bonds, and if your carbon or a nitrogen contains an extra hydrogen atom, then it is given by the position where there is an extra hydrogen as H, followed by the name of the compound. So let's go for what you see in your slides right now. First is 1 azapine. Why it is called 1 azapine? This is 1, 2, 3, 4, 5, 6, 7. So at first position, it contains an extra hydrogen. So it is known as 1H azapine. Okay, it is known as 1H azapine. Now let us go for the second one. Now go for the second example. Now let's see this N 1, 2, 3, 4, 5, 6, 7. 1 and 2. 1 and 2. There is no double bond at third position. It contains 2H, 4, 5 and 6. So that's why the next example is 3H azapine. Okay, understood? Similarly, if in 4H azapine, there is a saturation at the fourth position. That is one extra hydrogen at the carbon. That's why it is named as 4H azapines. And this is very important when you are studying your antipsychotic, anticonvulsant drugs. So this comes in that. Naming of these compounds come in that. So it's very important during your naming of your antipsychotic, anticonvulsant. Now that is a single nitrogen. Now let's go for your 2 nitrogen containing 7-membered ring. So 2 nitrogen containing compound. 2 nitrogen containing 7-membered heterocyclic compound. So let's see the first example. There is HN2 3. So this is that. Now what is the name? So since it has got two nitrogen associated with this compound, it is known as diazepine. It is known as diazepine. And the position 1 and 2 represent at the position where there is the nitrogen atom. So this is 1, 2 diazepine. Why it is written as 1H is written? So why it is written as 1H, 1, 2 diazepine? Because at the first position it contains an extra hydrogen atom attached to your nitrogen. That's why it is known as 1H12 diazepine. The next example is 1H13 diazepine, because the nitrogen is at the first and the third position and it contains an extra hydrogen at the first carbon. It contains an extra hydrogen atom at the first carbon. That's why it is known as 1H13 diazepine. So this is your nomenclature. Next is your 1,4 diazepam, which is your benzodiazepines, Benzodiazepine and all. They contain 1,4 diazepam. So 1H14 diazepam. So this nomenclature is very important to be known for you. That's the reason why I'm telling you. Please understand this properly. The saturated nitrogen is given the first priority, followed by your, and the position of your second nitrogen depends. That's why it is given 1, 2, 1, 3, 1, 4. And 1H represents the nitrogen at the first position contains an extra hydrogen atom. That's why it is known as 1H. It is a saturated nitrogen. That's why it is known as 1H, 1, 2, 1, 3, 1, 4 diazepine. So this is the nomenclature of your diazepine. Okay. Now, what is the next thing? What is the next thing? So if it is the same thing what I was explaining right now, depending upon the position 1, 2, 1, 3, 1, 4, 1, 5. So when the diazepine is combined with the benzene ring. So what is the next thing what they are telling? So if the benzene is fused to your diazepine, these basics are known as benzodiazepine family. In this, the compound, the nitrogen atoms are at the 1 and the 4 position. For example, clobazam, depending upon the position of your fused benzene, then the position of your nitrogen is at 1 and 4. So I'll be taking the examples later. So in benzodiazepine is nothing but when a benzene is fused to your diazepine analog. So basically 1,4 diazepines are used in your compounds. So here if you see the structure, so these are some of the structures of 1,4 diazepines. These are the structures of 1,4 diazepine. These are the structures of 1,4 diazepine. So it can here at, so 1, 2, 3, 4, 5, 6, 7 at the, so it is fused at 5A and 9A position. It is fused to your benzene at 5A and 9. So what is the examples? So if it is a diazepam means an anti-anxiety drug. Okay. So what is diazepam? Basically, it. So how can you name it? So there is an extra hydrogen at third position. There is an extra hydrogen at the third position. There is an extra hydrogen at the third one. That's why it is known as 3H benzodiazepine. Okay, methylated. These are the structures that you have to remember. That you'll be studying it in your. That you'll be studying in your MC, medicinal chemistry. So what is the basic structure of benzodiazepine? What is the basic structure of benzodiazepine, 1,4 diazepine? Just remember. So it contains a benzene ring which is fused to your, which contains an amide group, benzamide R, R1, R2, R3. Okay, this is the basic structure. This is a benzene ring, this is a benzene ring, and this one is R7. 1, 2, 3. This is 2, second position, depending upon the position they have mentioned. Okay, so what is benzodiazepine? Benzodiazepine, what is R1? It is methyl. Okay, R1 is methyl, R2 is nothing, it does not, R3 is also hydrogen, R7 means over here. So what is benzodiazepine? This thing is your methyl, this is your H over here, this is your H. So this is the structure of your benzodiazepine. This is the structure of your benzodiazepine. So what is the structure of oxazepam? Oxazepam, what is the structure? This is H, this is H, R2 is also H, R3 is OH. This is an OH. So this is the, and your R7 is mostly a chloro. It's an electron withdrawing group. Basically, it contains an electron withdrawing group. It contains an electron withdrawing group. It contains an electron withdrawing group. Okay, this is your basic structure of benzodiazepines, and I think it will, you have this thing in your medicinal chemistry. Now next is prazepam. Next is prazepam. So what does prazepam contains? It contains an CH2 profile group at the first position, hydrogen and a chlorine at the seventh position of your ring. Now what is nitrazepam? Everything is H. Everything is H. Only thing your seventh position contains an NO2 group. So this is nitrazepam. This is nitrazepam. This is important for you in your medicinal chemistry. It will come in medicinal chemistry. Okay, so please read this stuff. And next is lorazepam. Lorazepam contains what? Chloro at over here, chloro over here, and OH over here. So this is the structure of your lorazepam. When you see the chart, you can draw the structures of your corresponding benzodiazepines, 1,4-diazepines. Okay, so this is the structure of your diazepam and the synthesis. So how do you synthesize benzodiazepine? How do you synthesize benzodiazepine? Benzodiazepine synthesis, I think, is asked once. That's why I've introduced this particular this thing. So what you take? 2-amino 5-nitro benzophenol. So you take 2-amino. You take 2-amino. You take 2-amino benzo. This is benzophenol. Basic point. Okay. 2-amino 3, 4, 5-chloro. 2-amino 5-chloro benzophenol. This is the basic one. Yeah, and you treat it with glycine. You treat with ethyl glycine. What is glycine? It is an amino acid. NH2 CH2. Ethyl glycine means OOET. So what happens? It undergoes a condensation reaction in presence of your pyridine to give your corresponding compound. That is chloro. So your carbonyl group fuses with your amino group to form your linkage, the benzene ring. Then amine fuses with your, condenses with your ester group of your glycine. So you get your NH, C double bond O, CH2, CH2, NH2. So this is the structure. And the last step is you treat with your dimethyl sulfate. Dimethyl sulfate, and a base like sodium ethoxide, you will get your corresponding double bond CH2. So this is your structure of your diazepine, synthesis of your diazepine. So this is asked in your exam, so please practice it. Important from your examination point of view. Now let's go for some basic things. So this completes your portion for your heterocyclic compound. So this completes your portion for your heterocyclic compound. This completes your portion for your heterocyclic compound. Everybody, okay? So your portion for your POC2 is over. Your portion for POC2 is done. Okay. So today your portion is done. Everything is done for you. Okay. This completes your portion for your third year, fourth sem POC. It's done. Okay. Now let's go for the further thing. Some of the important criteria which I've tried to mention. This comes for 2 marks or a 5 marks question, combined question. Okay. So what is the first thing? Now, electrophilic substitution reaction. So pyrrole, as I said, it undergoes electrophilic substitution reaction, and it is more reactive than benzene. Why? Because the resonance pushes your away the electron density from your nitrogen towards your carbon, because the lone pair of your electron is shared with the carbon in the ring. So it increases your electron density in the ring. That's why pyrrole is more reactive than your benzene and your pyridine. This question comes in your exam. Okay, why? Now you understand. So if you draw, and whenever you give an explanation for all these things, please write the resonating structure and tell that the lone pair of electrons in your pyrrole is been distributed, is pushed towards your carbon. So in doing so, it increases the electron density in the ring, and the electrons are pushed towards the 5 carbon, whereas in case of pyrrole, in case of benzene and pyridine, the electrons are moved towards the 5 carbons, whereas in case of pyrrole, the electron is moved around across the 4 atoms. So there is more availability of the electrons in case of pyrrole as compared to that of your pyridine and benzene. That's the reason why pyrrole is more reactive than your benzene and pyridine towards electrophilic substitution reaction. And why pyridine is the least? Because in case of pyridine, the lone pair of electron is not available for the reaction, and nitrogen being electronegative, it pulls the electron towards itself, thus reduces the electron density in the ring. That's the reason why pyridine is the least reactive compared to that of your pyrazole and benzene. So please mention these things in your answer. Though some of the points may not be directly there, but listen to this and tell. So why pyrazole is more reactive than pyridine and benzene? You got the reason, because the lone pair of electrons in your nitrogen is been given to the ring. It increases the electron density in the ring. That's why it favors electrophilic substitution reaction more as compared to your benzene and your pyridine. So at which position? Preferably position is C2, the carbon next to your hydrogen. If there is an already substitution, then only it goes to the third position. Okay. At the second position, why does it prefers at the second position basically? So in doing so, the chances of coming of your electron on the heteroatom, that is a nitrogen, is less. So thus it's stable, and it has got 3 more resonating structure as you see in the green, whereas when the attack takes place at the C3, you got only 2 extra resonating structure, whereas it is when the reaction takes place at the second position, you get 3 more stable resonating structure. That's the reason why electrophilic substitution reaction prefers more at the second position rather than the third position. That's the reason why the electrophilic substitution reaction in case of your pyrrole prefers more at the second carbon rather than the third. Whenever the position is second is blocked, then only it goes to the third position. Most preferable position is at the second position as compared to that of the third, because at the third position, and whenever you are writing this explanation for any such reactivity aromaticity, you have to write the resonating structures of these compounds. It's mandatory for you to write the resonating structures of your compounds. Okay, please do have the practice of writing the resonating structures. I've been telling you from day one when I started the PUC. Okay, the resonating structures are very much important. Okay, so these are some of the reactions which we have studied in during our reactions of your pyrrole. So at the second position only it is preferred all your diazotization, sulfonation, nitration, diazotization, chlorination, iodination. Chlorination, iodination takes all the position because all the positions are electron rich. That's why it undergoes at all the positions. Okay. So now what is the next thing? What you see over here? This is also asked, and if you see in your syllabus, there is something called why you have to explain why pyridine is basic in nature. Why pyridine is a basic heterocyclic, okay, compound. Okay, it is structurally similar to that of benzene, where one of the methylene group is replaced by your nitrogen. So pyridine has 5 carbon and 1 nitrogen, all are sp2 hybridized. The p orbitals in the nitrogens and all the carbon lie in the same plane, so they are coplanar. So all these things are important to explain. The p orbitals result in delocalization of pi electron in a cyclic form, thus following the Huckel's rules, and maintain your aromatic character of your maintains the aromatic characters of your pyridine. So that's why the pyridine, why it is sp2 hybridized. The p orbitals lie perpendicular to the plane in a single plane, so there is a delocalization of electron. All are sp2 hybridized, and it has got 4 and plus 2 pi electrons in the ring. So all these things are satisfied. That's why pyridine is aromatic in nature. Now basic property. Why pyridine is basic? The nitrogen center of pyridine features as a basic lone pair of electrons, as a basic lone pair. Why it is used? Why it acts as a basic lone pair of the electrons? Because the lone pair of the electrons in the nitrogen in the pyridine does not get involved in your formation of your aromatic sexes. So it is free to form a coordinate bond or any complex with your acids. So it acts basically as a tertiary amine. So pyridine acts as a Lewis base by donating a lone pair of electron to your Lewis acids, like sulfur dioxide complex is formed. That's the reason why pyridine acts as a base. Very important for your examination point of view. This question comes in your exam. Okay, and it is must know in your guidelines as per your guidelines of the university. It is must know. Why this has to be learned properly? Because the lone pair of electrons are not involved in your aromatic sextet. It acts as a Lewis base because it forms a complex with your by donating a lone pair of electron to your Lewis acids to form a coordinate complex. So that's why pyridine acts as a base. Now let's go for the next criteria that is important. That's usually asked in exam. Okay, the reactivity. So question comes, write a note on reactivity and aromaticity of your furan, thiophene, pyrrole. Okay, along with benzene. Sometimes they do ask, compare with benzene. So what do you see the reactivity? Pyrrole is more reactive than furan, then thiophene and benzene. Okay, so when you are considering aromaticity, what you have to think? Degree, heat of resonance and energy has to be considered. Okay, electronegativity has to be considered. So that's the reason why thiophene is most aromatic compared to that of your furan and pyrrole. Your furan is least aromatic because it has got the least because it has got the least resonance energy, and second reason because furan has got oxygen which has got more electronegativity compared to that of your nitrogen. So this electronegativity plays also a major role in your reactivity also. It plays a major role in your reactivity also. Okay. So what do you see over here? So pyrrole and thiophene, pyrrole, furine are all of them are more reactive than your benzene towards your electrophile. Why? Why it is more electrophile? Because it has a lone pair of electron which can donate and increase the electron density in there. That's why these three heterocyclic are more reactive. But in these three, which one is more reactive? That is very important. Okay, thiophene is 100 times more reactive than benzene, and pyrrole is most reactive. Now if you see, pyrrole is more reactive compared to that of your oxygen or furan, and furan is less reactive than pyrrole because oxygen is more electronegative than your nitrogen. So your electronegative plays an important role in the reactivity also. Why? Because oxygen is more electronegative. Because oxygen is more electronegative than your nitrogen, so it pulls the electron more towards itself. And once it pulls the electron more towards itself, the charge is retained in your oxygen and it is not distributed towards the ring. That's why it reduces the electron density in the ring and reduces the reactivity. That's the reason why pyrrole is more reactive than than your furan. So electronegative plays an important role. This electronegativity reduces the electron density in the ring. That's why it reduces the reactivity. That is the reason why pyrrole is more reactive than furan, than thiophene, and your benzene. So this is the reaction. Okay, this is the reactivity of your thing, and this thing is asked in your exam. This thing is asked in your exam. This is the resonance energy through which you can consider your, according to the resonance energy, you can consider the reactivity also. Okay. So acidic character, why? As I explained, because it can react with the base to form your potassium salt, which can be hydrolyzed to give back your pyrrole on treatment with water. That's why your pyrrole is more acidic as compared to that of your thiophene and furan, which does not contain an replaceable hydrogen. So that's the reason why pyrrole is acidic in nature. So this completes your portion for your, this completes your